Yes, we can start. Happy to have Andrew Brown talking about growth and topology of counterexample of the strong.
Okay. Good morning, everyone. And first of all, thank you to the hosts in Patton at University of Warsaw and for all of you for coming. So today, I'll be talking about the Strong Eremenko Conjecture. This talk is different from the one that follows, which is not on the Strong Eremenko Conjecture, but is definitely worth going to. So I think I might be the first person to talk about transcendental dynamics at this two-week mini school. So I'm going to be introducing a few concepts and definitions that I don't think anyone else has done yet. So there will be a fair amount of low-level introduction to transcendental dynamics for mainly for students who I've spoken to who don't do transcendental dynamics. But hopefully there's something for everyone. And eventually I'll talk about stuff that is steaming fresh, shall I say. So first of all, F will be a holomorphic a transcendental entire function. Transcendental function, or I will be writing F. Okay, and when you see N, well, as an exponential, that is of F of. Okay, so iterating transcendental entire functions. Brilliant. Now, the factor set for a function or for a transcendental entire function F, right? F is the set such that the collection of iterates at the point Z, so where am I starting? Get them on. Normal. If you don't know what normal is, equicontinuity holds equally by the Arzela-Ascoli theorem. And if it helps, just think of the stable set. But I won't linger on that. And the Julia set is simply the complement in I. So your chaotic set. Okay. Up to now, nothing new for anyone who has seen complex dynamics. Whereas now I'm going to talk about the escaping set. And it's I for infinity rather than escaping. So the escaping set for transcendental entire function, well, it's just a base of infinity for your polynomials, whereas there's more to be said about it for transcendental functions. So it's Z such that the iterates tend to infinity as n goes to infinity. And for transcendental functions, certain things were noticed. So first of all, the things that were noticed back in the 20s, I'll move onto in a moment. But the first proper study of this, at least in the context of Eremenko's conjecture, was in about 1989. And it was shown that the boundary of the escaping set, so there we go, that the boundary of the escaping set is the Julia set for transcendental entire functions. And it was also shown that the Julia set intersected with the escaping set is non-empty, and that, oh, I've already written that, sorry. And these were Eremenko in 1989. Now, first of all, I mentioned that Julia noticed in 1926. 26, I'm very much paraphrasing, he didn't say it quite in the same accent, but let me get this, there are curves in the escaping set for some transcendental infinite functions. He wouldn't have used that notation, of course, but good examples, or I'll just say example for now. Take your standard exponential map, the real line exponentiates any real number, and again, you go to infinity. So the real line, but then we also know that 2 pi I up. All of these translates are in your escaping set. So what's that? R plus 2 pi I k. This collection is in your escaping set. Okay, so an actual example. The set that Julia studied, I think, was well, it was a sine family, but this one's slightly more easy. For 2. So you see where it says for 2 here, and I didn't write that down. There we go. Good spot, thank you. There we go. Hopefully I won't mess up any further. But the strong conjecture now. The strong Eremenko conjecture, you can say. And again, I'm paraphrasing, you wouldn't have said it in the same voice, but it's plausible that for transcendental type function f, the escaping set has the property that for any point in your escaping set can be connected to infinity within the escaping set. So plausible that for transcendental type f, as property gamma. Okay, so that is the strong conjecture. And so this was stated in 1989. Sorry, roughly the same time as this. So 89. This was shown false in a paper by Rottenfuser, Rucker, Remper, and Schleicher. And it was shown false by a counterexample. And so, just to write it out, let me make sure I get the right characters. There we go. I'll be writing this as triple RS as it comes up quite often. So there exists transcendental entire function f such that I of f contains no curve to infinity. Which is good, but to introduce the counterexample and to talk about it, I'll have to tell you all about class B functions. Okay. So, in order to talk about class B functions, I first need to bring up singular values. So, for polynomials who have a finite set of critical values, but for transcendental entire functions, It's a little bit more complicated than that. So critical values. So for your function f, simply f of z, when your derivative is 0. And the thing that you get with transcendental type functions are a different kind, asymptotic values. And these are when, so if you think about the exponential function, if you go down the negative axis, exponential of negative t, as you go further and further, tends to 0 whenever it's 0. So 0 is an asymptotic value for your exponential. So I'll write that down. Asymptotic values. So A. So anyway. Well, we have very complex plane. Okay. So that's the other kind of singular value that we need to pay attention to here. And so take these. So let capital AV that be a set of finite asymptotic values, and then put them all together by taking the closure of the union of your criticals and your asymptotics. Also, I should realize I'm lean in my handwriting. If it is too shoddy, do say, please. Okay. Okay, so now we've got this set of, where we have trouble. And I've seen one furrowed brow so far. Are there any problems or questions so far? Don't be afraid to ask. Okay. So if polynomials have just the critical values of interest, what's the closest we can get to that with transcendental type functions? And you can ask about when this set S is finite. So let me get introduced properly. So we call this the Spicer class. S. F. Okay, so that's one set of functions that you can look at. Whereas that could be a little bit restrictive. Well, if you allow for a little bit more, well, you get more. And what was introduced is the Eremenko Conjecture class B. And that is F, so the singular values are there. So, that the set of singular values is bounded in the complex plane. And of course, B for bounded rather than either E or L. You may wonder why I've bothered to mention both is, well, the class S is not the class B. So obviously every Spicer is B, but not every B is Spicer. Classic example is sine of Z over Z. This is in class B, but not in class S. Let's see don't differentiate to the public. And that's the more safe. if you look at the critical values here, then that's equivalent to saying you may as well find the solutions of tan z is z. Luckily, all the solutions to this are real. And then when you plug this back in, you find that you end up with sine over tan, which is just cos. And because we've only got real solutions, that's bounded by 1. So, concrete example for those who've never seen it before. And I've just brought up this whole class, like, they're studied, they're well, you know, they're of interest. But it turns out that you don't get everything you want, because the counterexample for the strong conjecture, which I just rubbed out, is class B. So even with this restriction on bounded singular values, you can still get these, I don't want to say misbehaving, but functions that don't give you the curves and the escaping test. So, for example, in triple RS is in class B. Am I drifting too far with the camera here, or is that fine? Right. Now,
I guess the for spider class you have.
I'd say yes. I don't see why not. So there is a subclass within B that I'll mention shortly, but it's to do with the order of growth that I know that you definitely get curves. Someone better qualified will probably have a better answer, but my gut feeling is yes. So it's a good question. I should look into that. As I'm sure if Lasso was in the room right now, he'd have the instant question. But anyway, now, how do you even come up with these counterexamples? So I've mentioned this. And what happens is that, so the reason you come up with what we call logarithmic coordinates is if you consider your transcendental entire function, and this is where I'm going to wave my hands a little bit for saying there is a black box that I use that gives me what I want. Don't think about it kind of thing. But if you have your transcendental F, and if you know that you've got your set of, what was it? If you have your set of singular values outside of the disk, or sorry, because you know that your set of singular values is contained in the disk set for F in class B, you can bound it. But then you also include F of naught and naught. Okay. Consider everything outside of this in the plane and take the pre-image. So you stay away from the origin and you get all of these simply connected domains here. And once you've done that, well, I've avoided 0 when F of 0, which means I've avoided 0 here. And no prizes for guessing when I said logarithmic coordinates. If you take a pre-image up here, then you get half plane here, and then you get periodic repetition. This picture will probably be slightly misguided, but roughly that's the idea. So this happens, and so I should leave that down there. And what we look for instead is we work up here and we get a capital F that takes us from these to these. And this is where the black box thing comes in. If you construct artificial domains here with certain periodicity, certain 2 by I periodicity, etc., etc. And if you make a map up here, then using work by Chris Bishop, I can't explain it very much, but I've just sort of been told this gives us the function. Keep working up there. You start up here and then you end up with a class B function down here. So this is my sort of child's play version, but so that's the idea. Start making, rather than these things that come up, you can come up with half scripts with certain wiggling and everything. And by analysing them, you can then say, there is a class B function downstairs with what we want. Okay, that feels very hand wavy. If anyone wants to interrupt and stop me or demand justification, do so. I'm going to carry on. Hopefully, what's next? Okay, now actually I can talk about the title. We're looking at the growth of counterexamples. I'll remind you of what order is for functions. So the order of f is this, which can be infinite. And then what we then say is if. So f is finite order row if and only if what F and Z. I'm going to break my own borders, sorry. There you go. Okay, and to briefly illustrate this for anyone who doesn't really order things, exponential and sine have order 1. Now you don't have to look far to get infinite order. Just compose the exponential with itself. Okay, and the reason I introduced this, well, it turns out the counterexample from triple RS is infinite order. So, counterexample in but there's a positive result. It turns out if F is class B and finite order, the strong Eremenko conjecture holds. Again, this is in triple RS. So an answer, partial answer to your question is, I imagine you're showing if spies are class functions are finite order, that would do, but I'm not going to try that on the stage.
I couldn't really know what here, but feature constructed counterexample in class rather than class B.
Ah, there you go. So that means, in terms of the strong Eremenko conjecture, your counterexamples in class B need to be infinite order. So one question that I've looked at is how close to finite order can you get? And there's various, so there's about 3 results, and I think in order to not, I need to talk about the topology part of my title at some point, so I'll skip over a couple of things, but basically, there's one result that takes triple RS and worked by the third R letter in 14. This says there exists a function f in class B such that there are no unbounded path connected components in and such that for all epsilon greater than 0, log is bigger. That's it. So you can get arbitrarily close. But now, the question that I've been looking at, and for some in the room will have already seen me talk about this, but there's a question in terms of providing explicit orders of growth and explicit counterexamples with the desired property. So for decreasing ether, such that ether tends to know both ether times log by 2 goes to infinity. Where is there a counterexample? That can be such that one of the questions, and every time I say, "Oh, this should be done by next time," there's a little bump. But another question to consider: be positive. Why all of the counterexamples? Why the negativity? Why not get a positive result out of this? So if we do consider a counterexample function, what can be said about its dually set or its escaping set, rather than just like, it's a counterexample, done? Why not study the topology of these sets? So the basic construction of the counterexample, let's see how long I've got. Okay. So these counterexamples that I've been looking at, we have these half infinite strips going off to the right. 5's about there. That's pi I. That's negative pi I. Then there's a conformal map taking you into the right half plane. So, we pick our tracts and our functions such that this is contained within the right half plane, i.e. you can talk about forward iterates and the points that stay within the tracts under infinite iteration. So if I talk about X, and if this domain is called T, so it's the set, so Z such that that's from F. And to talk about the Julia set of the function within this domain, you're going to look at the points that stay within that domain for all time. And by studying this, we find that the way that the main counterexample was first done was by a contradiction using that construction. And I don't have the full time to explain why it's a contradiction, but the way that it's done is that we take our geodesics in the right half plane, semicircles. The capital F is going down there. We construct in such a way that when you take the pre-image of these geodesics, they sit roughly here within this tract that we're working in. But then, if you remember, the tract is sat in here as well. So these geodesics are crossing over. Because I don't have the full time, if you can hopefully believe by our construction, these always sit here, and the forward image of this geodesic is this semicircular arc that cuts here, and the forward image of this geodesic is this one. Should there be a curve to infinity, i.e., you've managed to go all the way up here, in order to cross between this geodesic and this one, you've passed here twice. Okay. But these two semicircular arcs are the forward images of these geodesics. So that means you've got 1 and 2 distinct curves under a conformal map that are mapped here. So that means you had 2 curves here. And again, iterate this. You had 2 here. Oh, now you've got 4 here. All the way back, you have 2 to the K sub-arc. Yeah, and that's what gives the original contradiction. This topological thing that I've been looking at instead. So, okay, have one of these. The structure of the escaping set. Again, as I say, steaming fresh. It turns out that there are uncountably many pairwise disjoint subcontinua at these junctions. Again, I've very much phased out and hidden a lot of the specific, it may not be this particular one, it may be starting at a point further on, but that's the start of this topological question. And again, hopefully at the next time we talk, there'll be more to say, but yeah, this is where I'm up to, and these are the questions I've been considering, and hopefully you can understand and appreciate.
So how do you derive a contradiction from the existence of these curves?
So the contradiction comes from, if there was a curve starting and going along, because it must stay in here for all time, for all iterates, in order to be this escaping point. Should this curve go on, you would be able to go up to, let's call this like the kth wiggle. But you could do that for any k. And by back stepping, if you start at k, you have 2 here, k minus 1, you have 4. And then eventually you would have 2 to the k of these sub-arcs. That contradicts having a curve. There's a small argument, but that's what gives the original contradiction.
But so there's no curve, but there is some continuum.
This is the new discussion of what kind of continuum, and I think it looks like it's going to be indecomposable continua at these junctions. I think was it the canaster bucket handle? I think is approximately, but I'm not fully versed in that yet in order to give a proper full answer. So those are the two things I'm considering: the topology and continua here, and orders of growth. And I will stop here. Thank you. Any questions? No? Okay. Hello.
When we define singular values as closure of union of critical values and asymptotic values. So if we take a point which is limit point of say critical values,
Okay.
that point, is it necessary that that will be either a critical value or an asymptotic value? In other words, what is the justification in taking closure? Is it just for the safety that if we take a point outside it, it will be projection and we can have a covering, or really the limit points of critical values, for example, is actually critical value or asymptotic value?
To be honest, this isn't something I've had to question before, but see, I'm just thinking back now to the signs over Z example.
I don't think it needs to be.
No.
Because you will have to take the closures. I think there are examples where you don't really have neither a critical value nor an asymptotic value, but you're a limit of these ones.
Do you have an example?
I think.
I think this is a difference between singular values and singularities of the inverse.
Yeah.
So if accumulation points are not singularities of the inverse, which is critical values and asymptotic values. But the accumulations are still singular values, meaning that you need to remove them to have this covering. But they're not strictly speaking singularities of F line form. That makes sense. So that's why I take it.
So clearly you cannot define all branches of the inverse there. So in this sense, for sure, but it's not necessarily a singular an asymptotic value or a critical value. And I think there are examples. I wouldn't be able to produce one on top of my head.
Thank you.
Maybe a list. So, but this picture that you draw, how do you actually force the curve to have to be there, or what's the story behind it?
So we go into a loads of notation where we say, call this, or like the real value, which would be about there. We have this recurring formula between little ri and big Ri, and what's it? We end up with, I mean, we just set a list of criteria where we say f of these Ri is between here and it. Like, there's a whole set of bounds that we set, and we call it, like, at the moment, I think we've called it suitable data. But if you look at, so Triple RS paper and Dave Sixsmith's survey of class B functions, that gives a far more appropriate response than what I can do right now. But just by having this collection of data and saying, should this happen, then you can say, oh, these curves must do this, and you get the growth that you want. I don't know if that answers your question. Oh.
Okay, just one more question. We resume at 12:30. Last call in the morning.